Welcome to the final lecture of this course. In this lecture, we will be focusing on implementing singular value decomposition and principal component analysis in Python. We have learned about singular value decomposition and principal component analysis, or in short SVD or PCA, in previous classes. And what we are going to try to do is see how we can implement those numerical techniques PCA and SVD in the context of Python will be the major focus of what we will do in this lecture and module. So two things, singular value decomposition, SVD, and principal component analysis. Those are the two topics that we are going to be focusing on. Recall that how these techniques are used. Essentially, principal component analysis techniques is used for dimensionality reduction, and dimensionality reduction is one of the important tasks in machine learning domain. So we will be focusing on basically executing this task using the Python in this course and module. So let's get started with the SVD implementation in Python. What I have here in the screen that you see is a simple 3x2 matrix, and whenever we have a data, essentially the data will be represented in a matrix form where the rows will essentially correspond to the data sample. So the data point 1 is the first row, data point 2 is the second row, and the data point 3 is the third row in the matrix X that is shown here. And the columns essentially represent the features or the input of the data points that we have. Okay, so here let's begin with a very simple matrix which is shown here, which is 2 1 1 2 1 minus 1, and see how can we carry out the SVD of this matrix. We have discussed previously in the lectures there are two different methods to carry out the SVD. The first method is essentially taking this X vector and converting it into two different matrices, which is A and B. So what we are going to do is we will take this X and we will create these two matrices A and B, and the A matrix is essentially X times or X dotted with, or X dot product of X with X transpose, and B will be a matrix which will be storing the X transpose dotted with X itself, right. So these are the two matrices first we will create from the original data matrix X, and then we will do the eigenvalue decomposition of this A and B, and that will help us in doing the singular value decomposition. That's the approach number one that we can take to solve for the eigenvalue decomposition problem, right. So let's get started and see how we can implement. So this is the X. What we have done is we have imported numpy, and then using a numpy np.array, we have stored the matrix X, which is shown here, right. So let me execute this block of code that is here. We stored this matrix, and what we are going to do is from this matrix we are going to construct matrix A and B. As I discussed, matrix A is equal to X times X transpose, and matrix B is X transpose times X. Okay. So in this block of the code that you see now, we are taking this matrix X, and as we discussed previously that at the rate operator could be used to do matrix multiplication or dot product of two different matrices, right. So that's what we are using in the first line of the command that is here, and then we are calling the np linalg.ig function from the numpy, where we are passing on the matrix A itself. So we are essentially doing the eigenvalue decomposition of the matrix A. Okay, and we are going to be storing its eigenvalues and eigenvectors, and that we will use to construct U, V, sigma, and V, and so on. Similarly, you can see that we take the matrix B, and the V is defined, which is X transpose multiplied by X, and then we do the eigenvalue decomposition of the B matrix, and we store that in eigenvalue B, comma eigenvalue eigenvec B vectors, and again the np.linalg.ig function, which is a function in numpy, is used to do this eigenvalue decomposition of the matrix B. Now once we have stored that, what we do is we basically represent the different matrices that we are interested in, and the matrices that we are interested in is essentially U, sigma, and V. Okay, and what we do is we do this column swapping in an increasing order of the eigenvalues. So depending upon the different eigenvalues we do some rearrangement, and that helps us in essentially arranging and finding out the three matrices which are essentially the important component of the SVD implementation. So you can see that U is equal to I vec A and sigma and V has been now calculated by rearranging the matrices, and once we have been able to do that, we are essentially doing the SVD of the matrix X. Even though the eigenvalue decomposition operated on matrix A and B, but doing that decomposition we are able to find out U, sigma and V, which is related to matrix X. So let me go ahead and execute this code, and that will help you in basically seeing the value. So now you can see after the execution what we got corresponding to this eigenvalue. First comment we got this eigenvalues and eigenvectors of A. Similarly, we got eigenvalues and eigenvectors of B, and from there we are able to compute the three important matrices which are essentially the singular value decomposition of the matrix X. And so the matrix that you see, which is the U, right, sigma and V, are the three matrices which gives us the singular value decomposition of the matrix X that we have. So that's the first approach how we can use Python to compute or enable or do SVD, but there is also a simpler way to do this, and essentially turns out in NumPy you also have a SVD function that you can call. So this is linalg.svd. If you call that function and if you directly pass X, you do not have to do the intermediate steps like computing the matrix A, matrix B and taking the eigen decomposition of A and B. What you can do is using this function, you just need to simply pass the original matrix or the data matrix X, and it will automatically do all the steps for you and return the three matrices that you are interested in, and those three matrices are U, sigma and V. So here is a code block that actually implements this SVD using the SVD function that is there in the NumPy library that is out there. Okay, so what you see if I run this code block, right, it essentially takes the matrix X as an input in this function, .svd takes X as an input as a function and just gives the output which we are interested, which is essentially the U, sigma and V. So if you print U, sigma and V, you will see that this U, sigma and V are exactly similar to what we get for the other U. You can see that they look in the different orders, but essentially the U, sigma and the V matrices are same using the two different approaches, right? We can do A and B approach, and we can also do the SVD approach, and we can get that also done.